Hello, welcome to lecture 6. Today I am going to talk about circles. This is mathematics for class 9 based on NCERT syllabus. I am Sangam Banerjee and my details are given below. Today I am going to talk about circle. We have defined what circle is. It has a diameter, a line which passes to the center, and from center to the circle to any point on the circle is the radius. Okay, and diameter is, of course, is twice the radius. You can have line which need not pass through the center but apart from the center. These are called chord. Like PQ is a chord, RS is also a chord. Longest chord is the diameter. This is the longest chord. The chord is here, this will become shorter, this will be shorter, and so on, it will decrease. Okay, so longest chord will be the diameter. And you have a circle, you have a minor arc. This PQ is called the minor arc, and this is a bigger arc, is called the major arc. Okay, PQ is a minor arc is denoted by this curved line. PQ is a minor arc and PRQ is a major arc. The circle also has, you can make a segment, you can break it, you can, like a chord, this is a chord. So this is called the minor segment, the smaller portion, and the bigger portion is called the major segment. So similarly, if you can cut it from, say, from the center to these edges of the circle, so this is the minor portion is called the minor sector, and this is the major sector. Okay, so difference between segment and sector is, in segment it is a chord along a straight line you cut, but in a major in a sector you cut from the circle to the center and again from center to the circle. This portion is called the minor, this is the major. So center word, sometimes people use CNTR or CNTRE, just I may sometime make mistake in writing it, but this is, one is English, one is American. Theorem 10.1. So we go to theorem now, 10.1. Equal chord of a circle. Okay, this is a chord, AB is a chord, CD is a chord, and they are of same length. AB is equal to, so I have put 2 dash. Okay, and this is a radius, so this radius is same as this radius, so these are all similar, 1 dash. Okay, so equal chord of a circle subtend equal angle at the center. So this chord will subtend some angle, say alpha. Since the chord is same, this will also be the same. Okay, this is also will be measure alpha. Okay, also this is alpha, this is beta, alpha is equal to beta. Okay, so and also since this is same radius, and this, so from side, triangle AOB is equal to triangle COD. So angle AOB is equal to angle COD from CPCT, that is corresponding part of congruent triangle. Okay. 10.2. If the angles subtended by the chord of a circle at the center are equal, then the chords are equal. We'll use this. Suppose this is one chord. If the angle is same, then the chord length is same. It's vice versa. Again, you can use this CPCT and show it. Okay, from that show that two triangles are congruent from CPCT. Okay, you can say the side angle is given to you. You are saying same angle, and this angle is given. So side angle side. So these triangles are congruent. So this side is equal to this side. Okay, you can prove it whichever way you feel is convenient to you. Okay, now let us see what theorem 10.3 says. The perpendicular from the center of a circle, okay, if I draw a perpendicular from center of a circle to a chord, bisects the chord. This we have seen. This is an isosceles triangle. If I draw a perpendicular, then it is. So similar thing here also you can show that this AM is equal to MB, BM. So from, suppose I draw a perpendicular and I draw a perpendicular line, bisect it. Okay, of course it will bisect if you draw a perpendicular line from with a compass, but anyway this is from right angle triangle, hypotenuse and side. So this is right angle triangle, your hypotenuse is radius, is same for both the triangle. This triangle 1, say this triangle 2, hypotenuse is same, and side is also same. This is a common side. So for a right angle triangle, if hypotenuse and one of the side is same, this triangle is congruent. So if this is congruent from CPCT again, this length will be equal to this. Okay, AM is equal to BM. Okay, now theorem 10.4. The line drawn through the center of a circle to bisect the chord, if I bisect this and this is equal to this, if I bisect it, is perpendicular to the chord. So earlier, if it is perpendicular, then this is bisected. Now if this is two equal, then this has to be perpendicular. OM is perpendicular to AB. So again you can prove that this triangle is congruent to this triangle, that is triangle AOM is perpendicular, is congruent to BOM, because this side and this side is same, is bisecting, it is saying bisecting, so this is also same, and this is a common angle from side. So these are congruent, and then you say that okay, this angle and this angle are same because they are congruent. So but this is a straight line, so linear pair of angles should add up to 180. So both are same, so 180 divided by 2, this will be 90. So if it is 90, then OM should be perpendicular to AB. Okay, you just write it what I have said. So if you understand, you first understand and then don't try to mark whatever is written. You write it in your own words, and that is always better. Theorem 10.5, there is one and only one circle passing through three given collinear points. Non-collinear points means triangle. Collinear means straight line. If they are collinear means it will three lines in collinear straight line. But if they are collinear means they will form a triangle. There are 3 points, triangle require 3. Okay. So we have proved earlier that any triangle can be circumscribed. This was proved earlier. Now theorem 10.6, equal chords of a circle are equivalent from the center. Okay. Equal chord. Suppose this chord AB and DC are equal, so they will be from O to this midpoint here and from O to this midpoint P will be same. So if suppose I have one small and one big, then it will not be same, because this will be smaller and the small chord will have a bigger. But if they are exactly same, AB is equal to DC, then the distance between OM and OP will be same. That again you can prove by showing that this triangle is congruent to this and this triangle is congruent to this. This is a common side. Or if this triangle is congruent to this, height of this triangle has to be same. So you can again prove it. Okay. You can break into this triangle is congruent. Why? Because this side, this chord, this is a radius, this is radius. So again this is radius, and this is chord. So side, these two triangles are congruent. So once they are congruent, the height of the triangle has to be same. Okay, these are very simple. I am not writing all the steps because these are so obvious. So you please write it yourself. Now theorem 10.8. The angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. So from the center, this arc is there, this is the angle. So this angle at the center is double the angle, is the angle from any part, remaining part of the circle. If my point is say here and I draw from P to this point and then from this point to Q, or here I have drawn from P to say point A and A to Q. So this angle will be half of this one. If this is A, this will be A plus A twice A. So how do you prove it? It is very easy to prove. Let us not see the step. Okay. First let us see pictorially how to prove it. This is radius, this is also radius. From center to any point on the circle is always radius. So this side is equal to this side is equal to this side. Okay. Now I draw a triangle here. Okay. Once I draw a triangle, this becomes an isosceles triangle. You see this side and this side is same. So since I have bisected this angle A, so this will be half A, and so in an isosceles the opposite angle should be equal. So if the length are equal, this length is equal. So this is half A, so this also will be half A. Okay. and then sum of this, what is the exterior angle? This is I take this triangle, okay, AOP triangle, and I extend this line. So this is the exterior angle. Exterior angle is sum of opposite two interior angles. So half A plus half A. So this angle is A. So similarly for this triangle also you can do and show that this is also A. So now this angle is twice A and this angle is A. So we have proved it. So this is what we have done here to prove this angle O is twice of angle A. So angle O I can always write POQ. This is short because of laziness. I have just written O. Actually you should write POQ so that it's more correct. So angle POQ is twice angle A, angle PAQ. Okay. We can always keep a track. What you are writing you know, but later on you can correct it. So extend, say whatever I have said here, BOP or BOQ, this is the exterior angle. So this is a step where I have written BOQ is angle OAQ plus angle OQA. That is what I have written. Okay, what I have said I have written. So angle BOP is angle OPA plus OAP. This is what I have written here, and since OP is equal to OA is equal to OQ, these are all implies angle OAP, this is angle OAP is equal to OPA and OAQ. Just see from here what I have said is equal to OQA because it's an isosceles triangle. Okay, so angle BOP, this angle BOP plus angle BOQ is angle O. This angle plus this angle is angle O total. So that's what I have written. Just freeze it and see this step. So angle O is equal to, okay, angle O means here angle POQ is equal to twice of angle A. Angle A is PAQ. Okay, now this is the second case. Suppose here this angle is less than 90, but suppose it is 180, less than 180 degree. And now suppose this line PQ is 180 degree, and if I join this any point here to here, so this will be half means this will be perpendicular, this will be 90 degree. So if this is 180, this has to be 90. So I have written here curve, but you should write square here. Okay, square means it is perpendicular. So this will be perpendicular by same argument. But there is case 3, that suppose it is more than 180, then what is this angle? So I bisect this and bring it here, and I make two triangles here. This is the radius, this is radius, this is radius. Okay, and since this is isosceles triangle, this is exterior angle. Suppose I extend this to B, then this becomes an exterior angle. So exterior angle is half of, this is A, so half of A plus Q, and similarly for this triangle it will be half of A plus P. Okay, this angle P, half of angle A plus, this is half of angle A plus half of angle P. Okay, go slowly since you can always freeze it and think about it. So that's what I have written here. Angle BOQ, which is an exterior angle, is half of A plus Q, and BOP is again half of. So angle P will be similar because this is again isosceles triangle. This is half of A, so this also will be half of A. Similarly, this will be half of A. So now I can say what is angle POQ. This is angle POQ. So POQ is equal to angle POB plus angle QOB, okay, or BOQ, these two angles. I add it. This angle we saw it was half of A plus P, and this is half of A plus Q. P and Q are both half A, so half A, 1A. So this angle O is twice of angle A. Okay, go through it. It is a very simple step. I have not drawn maybe properly, but you draw yourself and check it out. Now theorem 10.9. Angles in the same segment of a circle are equal. Okay, So this is a minor segment and this is a major segment. In the same segment, this angle, suppose there are 2 points P and Q. The angle from any point A or point C to P and Q, the angle will be same. So from earlier theorem, we know that this POQ is double of PAC or it is double of PCA. Okay. From earlier theorem 10.8, this theorem, angle O is double of angle A. Here we have shown. So since both are equal, this is also twice PAQ, this is, so 2 cancel, so angle PAQ is equal to angle PCQ. So angle A is equal to, so any of them you can, from this theorem, says that it is not very specific for this segment. And if you have we have shown that if you have a diameter, then it is 90 degree. Okay, this example, they can ask you an example. In theorem, we have not proved it, so here we prove it. Angle POQ is 180 degree is equal to twice, this angle is twice of angle A or angle B or angle C. So that's why I have written twice of angle A or angle B or angle C. The middle one is, the center point is C, and PQ at common point, this point. So I write 180 degree, this is twice angle A or equal to twice angle. So since 180 degrees twice this angle ABC implies angle ABC has to be 90. 90 into 2 is 180, 90 into 2 is 180. So these are 90 degrees. This is true for any other point on the semicircle. Angle in a semicircle, so you can say angle in a semicircle, if these two endpoints are on the diameter, is a right angle. This angle is always a right angle. So you should draw not as an arc but as a small square here. Theorem 10.10, if a line segment joining 2 points subtends equal angle, if they subtend equal angle at 2 other points lying on the same side of the line, okay, this is the line AB, say 1 point here, another point here, same side, they have equal angle. Same side line containing the line segment, the 4 points lie on the circle, these 4 points A, B, C and D. But if suppose it is say point E or point E prime, so this angle will not be this, okay. This angle is this angle and this angle will be slightly larger and this angle will be slightly smaller because it is more sharper. This is not so sharp, this angle is more than this. So since angle AEB and angle AE prime B is not equal to ADB, so only this, that's what, and then they are said to be concyclic. Okay, now theorem 10.11. It says the sum of either pair of opposite internal angle of a cyclic quadrilateral is 180. The opposite angle, the sum of opposite angle of a cyclic quadrilateral, cyclic means touching, each vertex is touching the circle. So the opposite, this and this opposite angle sum is 180. This angle plus this angle is 180. So if it is so, then it is, of course, if you can prove that these are 180, these opposite angles are 180, then it is a cyclic quadrilateral. So how do you prove it? Here we prove, suppose I take this AB and I just draw this triangle and this triangle common. So then I know that since this is a common chord, this angle will be equal to this angle which we have seen just earlier. And similarly, if I take BC as a common chord, I can again draw a triangle, this triangle, triangle DBC and triangle ACB. This is a common. So one common chord here I have taken, another common chord here I have taken. Okay. So for AB, this AB, this A, this is AB, okay. This ACB is equal to ADB, because here one dash I have put, so they are same. And similarly, if I take BC as a common, this angle BC is common, okay. This angle which is subtended, double dash, this is equal to this double dash, okay. For BC is this. So now I add these two, angle BAC plus ACB, if I add them, is equal to nothing but ADB plus BDC. What is ADB? ADB plus BDC. So this is a total angle. Okay, so this is angle D. But I know that BAC, this is BAC, the sum of all internal angle has to be 180. I know. So BAC plus ACB plus CBA has to be 180 degree. So this BAC plus ACB I substitute as LD here. So angle D, sometime I make mistake saying LD, but it is angle. Okay. So maybe I might have said previously. Angle D plus angle B equal to 180 degree. So that means this angle, opposite angles are 180 degree. And we know from quadrilateral all the sum of internal angle has to be 360. So here LD plus LB, I substitute it as 180, take it here, 360 minus 180. So remaining angle A plus angles is 180. So this is also opposite angles are 180. So once if you can show that they are 180, then the quadrilateral is cyclic. Now theorem 10.12, if the sum of the pair of opposite angles of a quadrilateral is 180, the quadrilateral is cyclic. That's what we said. Okay. Here is saying for a cyclic quadrilateral, some of the we have proved. So we can prove this also in a similar line. Okay, you have understood. If you have understood this, you can prove this also very easily. It's the same thing. Okay, now example 10.813. In this figure, AB is the diameter of the circle. CD is a chord equal to the radius of a circle. This is a given. Okay, this is AB is a diameter. CD is a chord equal to the radius from O to D, O to C and C to D, they are same. So it is an equilateral triangle. So angle between them will be 60. Okay. AC and BD, AC is this one and BD is this chord. Okay, there is a chord here, BD. When extended, it will intersect at E. When extended, intersect at point E. Prove that angle is 60 degree. Prove that this angle is 60 degree. This is to be solved. So triangle ODC is equilateral, as I said. This is the same length of a radius. This is radius, this is radius. So this is equilateral. So that means all angle here are 60 degree. And angle ACB, since this is 180 degree, this one. Okay. So we have seen that this will be twice the angle from any if I suspend this line to A and B, okay, it will be half. So since this is 180, this will be 90, which we have proved it, okay, for a semicircle. So this is 90, angle ACB is 90 degree, and angle CBD, this is angle CBD, okay. So you see here, this from center, if you subtend this angle is double and CD is a common here than this. So if this is 60, this has to be 30. Okay. So this will be 30, half of COD is 30. And this ECB also. So this one, since this is 90, ECB will be also 90. So this is 90. So if I take this triangle, I have here 90, here I have 30. So remaining will be, so angle E will be 60. Okay, because 30 plus 90 is how much? 120. But sum of all internal angle has to be 180. So you have to add 60. So angle is 60. Okay. So also quadrilateral OCED is non-cyclic because this is total, this is 60 and this is 60. So it is the sum of opposite angle is not becoming 180, but it is 120. So we saw that to be cyclic, sum of opposite angle has to be 180. Okay, now example 10.8.6. You have been given a quadrilateral, this figure, and you have been told that bisect all this angle A, B, C and D. So you know how to bisect. I think you, with a compass, you draw a circle, then draw an arc, and then you can, from this point and this point you take, and again, so you can bisect it. It is very simple to, we have I have told earlier in earlier lecture. So you can always bisect this by compass. So when you bisect this and extend it, you will get one quadrilateral, one figure here, and it has been asked prove it is a cyclic quadrilateral. For proving cyclic quadrilateral, angle, the opposite angle has to be addition of this angle F plus angle H has to be 180, and angle E plus angle G has to be 180. So this is what we have to prove. Okay. So if I take this triangle, say we start with H. Okay. So angle H is an exterior angle of this triangle. A, this point H and B. Okay. So angle H, the exterior angle is sum of two opposite internal angle. Okay. Half of angle A and half of angle B. This is what we have written. Similarly, F, okay, if this is a triangle, so exterior angle F is half of angle C plus half of angle D. This is what we have written. So if I add this LH plus LF, I will get half of LA plus LB plus LC plus LD. Okay, A, B, C, D. But what is sum of all the internal angle is 360 degree. We know it. So half of 360 is 180 degree. So angle this, angle H, this is the angle H. Okay. If this exterior angle is H, the interior angle will be is a vertical opposite angle. So we have found this H. This is also H. Okay. Angle exterior angle F is also internal angle F. So angle H plus F. So similarly, you can prove this angle E plus angle G is also 180 degree. So now let us summarize what we have done in the last two lectures. Okay, we have seen to circumscribe a polygon by a circle, then bisect the sides, and if the bisector does not meet, intersects, does not meet at a single point, then one cannot circumscribe a polygon. Okay, which we have seen it. To inscribe a circle in a polygon, you bisect angles. And from the point where bisector intersects, draw a perpendicular line to any of the side. The distance between these two intersection points is the radius of the circle to be inscribed. Okay, go through it. Then we have seen that interior sum of all the interior angles of a polygon is this, if the side is n, so n minus 2 into 180. And sum of exterior angle of a polygon is always 360 degree. This was a definition of a parallelogram. Okay, this side is this 3 dash is this is 4 dash. They are equal. They are bisecting, which we have seen it. For a rhombus, we saw that they are perpendicular bisector. For a square also similarly. And if we have also seen that if there is a midpoint, this side, triangle, from the midpoint to this midpoint, if you join, these lines are parallel. We have seen it. So if they are parallel, then this F will be in the midpoint of AC. Okay, this is the two theorem, vice versa. We have seen that if they are equal size chord, length chord, then the angle subtended theta 1 equal to theta 2. From CPCT congruence, we have seen this. Then if you draw perpendicular to this chord, this will bisect. That also we have seen it. We have seen that if the angle subtended from O to these 2 points P and Q, and if we subtend from any other from this upper segment, then this angle will be double of this angle. Okay, angle O is twice of angle F. And if it is 180 degree, this angle is 90 degree. So if this is more than 180 degree, this angle will be opposite. This will be more than 90 degree. This here it is less than 90 degree. Okay, if it is less than 180 here, this will be less than 90. If it is 180, this will be 90. If it is more than 180, this will be greater than 90. Okay, just have a look. And cyclic, if the diagonals, sum of the angle, okay, opposite angles, sum of them has to be 180. LA, angle A plus angle C and angle. And sum of all the internal angle of a quadrilateral is 360 degrees. So we have covered chapter 10. This is a summary of chapter 10 in your book, so that you get convinced that yes, we have covered. This is from your book. A circle is a collection of all points in a plane which are equidistant from a fixed point in the plane, that is radius. Okay. Equal chord of a circle subtends equal chord, as we have shown that subtend equal angle at the center. If the angles subtended by two chords of a circle at the center are equal, then the chords are equal, the length are equal. If the angle subtended at the center is same of the two chords, then the chord are same. The perpendicular from the center of a circle to a chord bisect the chord. We have seen it, because in isosceles triangle also we saw the similar thing. If you drop a perpendicular, it bisects. 5. The line drawn through the center of a circle to bisect a chord is perpendicular to the chord. Okay, this also we have seen it. It is easy to prove. There is one and only one circle passing through three non-collinear points. That also we have checked it. Okay. Equal chord of a circle are equidistant from the center. If the chord length are same, we have seen it, then the distance from the center to the chord is same. Chords equidistant from center of a circle are equal. If they are equidistant, then also they will be equal. They are equidistant from the center. As you move away, at the center is the biggest chord, that is diameter. As you move away from the diameter, from the center, the chord length will reduce. Okay. If two arcs of a circle are congruent, then the corresponding chords are equal, and conversely, if two chords of a circle are equal, then the corresponding arcs are congruent. Obviously, if two arc is same, then the chord drawn on that arc will be same. Okay. Congruent arc of a circle subtend equal angle at the center. It's similar to chord. Equal chord subtend equal angle. So here congruent arc also will do the same thing. Okay. 11. The angle subtended by arc at the center is double the angle subtended by it at any point on the remaining part. It's the same thing, no? Angles in the same segment of a circle are equal. That we saw in the same, say from point A to B, if I in the same segment, say upper segment, okay, a major segment, any point I take and draw to that point A and B. From any point of the circle, they will have the same angles. So angle in a semicircle is a right angle. We have seen this. If a line segment joining two points subtend equal angle at two other points lying on the same side of the line containing the line segment, the 4 points lie on the circle. This we have proved it. Okay, a line segment you have taken AB, and then there is another point, say C and D. They will subtend same angle, and so they will all the 4 points will lie on the circle, because the other two will subtend with respect to this chord subtend same angle. The sum of either pair of opposite angles of a cyclic quadrilateral is 180. This also we saw, sum of either pair of opposite. And if the sum of pair of opposite angle of a quadrilateral 180, the quadrilateral is cyclic, the vice versa. So we have finished the chapter on circle. Thank you. See you in the next lecture.